What if I told you that using modern asynchronous JavaScript might actually be the exact reason your web application is freezing up?
Oh, man. Yeah. That is a bold claim, but it happens all the time.
Right. I mean, you've likely been in this exact situation at some point just this week. You're on this complex web dashboard, you click a button to pull down a massive report.
Like financial analytics or
Yeah.
user data or something.
Exactly. And a sleek little loading spinner appears on the screen. You expect this perfectly smooth wait.
But instead, the entire browser tab just completely locks up.
Yes, you can't scroll, you can't click another tab, you can't even highlight the text on the page.
And that spinning loading icon is just frozen dead in midair. It creates this moment of pure user panic, honestly.
It really does.
You sit there wondering, did I break the system? Should I force refresh? Is my machine just completely out of memory?
And then, 3 or 4 agonizing seconds later, the data suddenly renders, the page snaps back to reality, and everything acts perfectly normal again.
Which is incredibly jarring.
It is. So today we are going on a mission to figure out the architectural root cause of that freeze. And more importantly, how modern browser features can actually solve it.
Yeah, this is a great topic.
We're doing a deep dive into this fantastic piece of source material published on tech-reader.blog. It's by Aaron Rose, and it's titled The Secret Life of JavaScript Parallel Processing with Web Workers.
And what I love about this source is that the author takes this deeply technical architectural problem and grounds it in a narrative.
Yeah, it makes the abstract concepts highly tangible.
Exactly. So we are introduced to two software engineers who are navigating this exact issue.
We have Margaret, who is a seasoned senior engineer, and she's mentoring her junior colleague, Timothy. And the setting is incredibly atmospheric.
Oh, it's so good.
Right. They aren't in some sterile neon-lit tech hub. They're working out of a grand Victorian library in London.
Big dark mahogany desks,
Yeah.
towering bookshelves, absolutely quiet.
And the author uses this setting to emphasize that code quality here isn't just a metric to hit for a sprint. It's a matter of, deep craftsmanship.
Which serves as a brilliant contrast, I think. You have this beautiful 19th century aesthetic, but the problem Timothy is slamming his head against is a cutting-edge 21st century V8 engine performance bottleneck.
Okay, let's unpack this. Timothy is staring at his screen, and he is just incredibly frustrated.
Totally understandable.
He built this dashboard that fetches historical analytics data. He hits the button, and his beautifully designed CSS spinner—
Which usually runs at a flawless 60 frames per second, by the way.
right, flawless.
Yeah.
But it drops to a dead halt for 3 seconds every single time the data payload arrives.
Yeah.
So he turns to Margaret and explains that he spent 3 days specifically optimizing the main thread to prevent this.
Because he followed the playbook for modern performance. The source details how he implemented an intersection observer to track element visibility without causing layout thrashing.
Which is standard best practice.
Exactly. And he used a resize observer to handle responsive shifts without bogging down the rendering pipeline. He was actively writing code designed to keep the user interface fluid.
And crucially, he explicitly tells Margaret that he used async await for his data fetching.
Ah, yes, the trap.
Wait, hold on. If Timothy explicitly told the code to use async await, literally commanding the engine to handle the fetch asynchronously, shouldn't that guarantee the code is running harmlessly in the background? Why is the UI completely dead?
Well, that assumption is exactly the trap. Margaret identifies it immediately. She calls it the async illusion.
The async illusion. I like that.
It's a fundamental misunderstanding of what asynchronous syntax actually guarantees in JavaScript.
Okay, break that down for me.
So the network request itself, reaching out to a server, establishing a handshake, downloading the data over the wire that is genuinely asynchronous,
Right?
the browser's networking layer handles that part, which leaves the rendering engine totally free to animate that CSS spinner.
Okay, so the download completes over the network. The data arrives safely at the browser. What's the roadblock?
The roadblock is the payload size and what the browser actually has to do with it once it arrives. Timothy isn't pulling down a tiny configuration file.
No, he's requesting a massive 50-megabyte payload of raw enterprise analytics data.
Exactly. And the exact millisecond that massive string of text finishes downloading, the browser has to physically convert it into a structured, usable JavaScript object.
Wait, if the data is just raw text, why does the browser care? I mean, text is text. Why does simply reading a text file paralyze the whole user interface?
Because it isn't just reading. It is translating and building. The process of parsing JSON requires intense lexical analysis.
Oh, right, because it's not just a string to the engine anymore.
Exactly. The JavaScript engine has to tokenize every single character. It reads an opening curly brace and has to, like, allocate a specific block of physical memory in your computer's RAM for a new object.
Wow.
Yeah. And then it reads a quotation mark, identifies a string, figures out where the string ends, assigns it as a key, and then links it to a value.
Doing that for a few lines of text is instantaneous, sure.
But doing that for 50 megabytes of nested data points,
Yeah.
that is a monumental computational task.
And that parsing operation, unlike the network download, is completely synchronous.
Yes. It happens squarely on the JavaScript main thread.
Yeah.
And to understand why that instantly freezes a web page, we have to look at the architectural constraints of the language itself.
Because JavaScript fundamentally can only do one single thing at a time.
Right.
Which honestly feels completely counterintuitive in an era where our laptops have, 12 core processors?
Oh, absolutely.
Why can't JavaScript just multitask and parse the text on a different core while the UI stays active?
Well, if we connect this to the bigger picture, it really comes down to historical context. JavaScript wasn't designed for heavy enterprise computing.
Right, it was just for browsers in the 90s.
Exactly. Brendan Eich created the first prototype of the language for Netscape Navigator in just 10 days back in 1995.
10 days? That's still wild to think about.
It is. And its original purpose was incredibly lightweight. It was just meant to validate a form before submitting it, or maybe, swap out an image when you hover over it.
It was built to be a simple scripting tool, nothing more.
Yeah, and single-threaded architecture was chosen because it is inherently safe and predictable.
Safe how?
Well, think about it. If you have multiple threads trying to change the exact same button on a web page at the exact same millisecond, you get catastrophic race conditions.
Oh, right. The browser would just crash.
Exactly. So the ironclad rule was established. One main thread, one execution context handling the document object model, the user inputs, and the JavaScript logic.
Margaret in the article uses a great analogy for this. She says the main thread is like a single chef working alone in a kitchen.
Yes, I love that part. It can only do one thing at a time.
And if we apply that to the async illusion, using fetch is like putting water on the stove to boil.
Right, the chef can walk away and chop vegetables, which is animating the spinner while waiting for the water.
That part truly is asynchronous.
But then comes the breaking point.
Calling response.json on a 50 megabyte payload.
Yeah, that is like dumping 50,000 carrots into the middle of the kitchen.
Wow.
The chef has to stop everything. No food gets cooked, no CSS spinners animate until every single carrot is chopped.
Let me try an analogy here, too, just to help visualize why Timothy's dashboard is locking up.
Yeah, go for it.
Think about ordering a massive, complex piece of furniture from IKEA, like a giant floor-to-ceiling wardrobe.
Okay, I'm with you.
You go online and pay for next-day delivery. The delivery process itself is incredibly fast and asynchronous. The delivery driver pulls up to your house, drops these huge, heavy, flat-pack boxes on your front porch, and drives away.
Right.
You didn't have to pause your entire life while the truck was navigating traffic.
And that represents the fetch request.
Right.
It happens in the background.
Right. The delivery was async. But now, those flat-pack boxes are sitting in your living room. Those boxes represent the raw, unparsed 50 megabyte text string.
Ah, I see where you're going with this.
To actually make that wardrobe usable, you have to assemble it. And in this scenario, you are the JavaScript main thread. Because you work alone, you have to stop your entire life for 3 uninterrupted hours to build it.
You're just totally occupied.
Exactly. You can't cook dinner, you can't answer the phone, you can't even walk the dog. You are sitting on the floor with a tiny Allen wrench, parsing the instructions and building the structure.
That is a perfect way to put it. The fast delivery gives the illusion of speed, but the assembly phase is where your household completely grinds to a halt.
Yeah.
In a web browser, the assembly phase is the JSON parsing. And while the main thread is building that data structure, it cannot listen for a mouse click, it cannot register a scroll wheel movement, and it absolutely cannot update the pixels on the screen to rotate a CSS spinner.
So how do we get this wardrobe built without stopping our lives? Timothy clearly needs a way out because reducing the data size just isn't an option for an enterprise analytics dashboard.
Right, and this is where Margaret walks over to a whiteboard in the library and introduces the modern web's escape hatch. She writes down 2 words, web workers.
Web workers. Let's break down what a web worker actually is on a technical level. Because we just established that JavaScript is strictly single-threaded by design. How do we suddenly introduce parallel processing?
What's fascinating here is how browser vendors recognized the single thread limitation and built a backdoor at the browser level, rather than changing the core JavaScript language itself.
Oh, interesting. So it's a browser feature, not a language feature.
Exactly. A web worker allows a developer to request that the browser spin up a completely separate, parallel operating system thread running in the background.
Returning to our IKEA metaphor, this is like hiring a dedicated contractor and putting them in a detached garage.
Yeah.
You take the raw, flat-pack boxes from the porch, slide them under the garage door, and tell the contractor to build the wardrobe.
And the most vital part of that metaphor is the detached garage. The web worker operates in a completely isolated execution context.
Meaning it's totally separate from the main page.
Right. It has its own isolated memory space. It does not have access to the house. It cannot touch the DOM. It cannot manipulate HTML elements. And it cannot see the user interface.
Which protects that original rule we talked about. It prevents race conditions because the worker in the garage can't accidentally paint over the living room walls while the main thread is trying to hang a picture.
Exactly. The main thread retains total control over the user interface, but its role fundamentally shifts.
How so?
Instead of doing the heavy lexical analysis of the 50 megabyte payload, the main thread receives the raw text from the network, hands it off to the worker, and immediately returns to animating the CSS spinner at a flawless 60 frames per second.
So the main thread acts strictly as an orchestrator, it just delegates the assembly.
Right. It just waits for the web worker to finish the heavy lifting and send back the fully structured, ready-to-use JavaScript object.
Okay, let's follow the data here because this raises a massive logistical problem.
Oh, I know where you're going.
If the main thread and the web worker are in completely separate, isolated environments with entirely separate memory spaces, how do they actually communicate? I mean, I can't just yell through soundproof drywall.
Yeah, they communicate through an event-driven system using an API called postMessage.
Postmessage. Okay.
The main thread sends a message containing the raw data, and the worker listens for that message. When the worker is done, it uses postMessage to send the finished object back.
Sounds simple enough.
But the underlying mechanics of how that message is delivered is where Margaret introduces her advanced architectural caveats.
Because passing a tiny text string is easy, but Timothy is passing 50 megabytes of data.
Right. And that triggers a browser mechanism called the structured clone algorithm.
Structured clone algorithm.
Yeah. Because the main thread and the worker do not share memory, the browser cannot simply pass a reference or a shortcut to the data. It has to physically copy the entire payload.
Wait. If I hand a 50 megabyte raw text string over postmessage and the browser physically clones it, doesn't that mean the data is briefly duplicated in the user's system?
You nailed it.
My 50 megabyte payload suddenly spikes my user's RAM to 100 megabytes while it's being handed off.
That is the exact trap. For a 50 megabyte payload, a modern computer can usually absorb that temporary RAM spike. But Margaret challenges Timothy to think about scale.
Because apps always grow?
Exactly. What if the dashboard evolves to pull down 200 megabytes of data? The structured clone algorithm will duplicate that to 400 megabytes.
Wow, that sounds like a massive memory leak hazard. Eventually, the browser's garbage collector is going to have to step in and aggressively delete the duplicate data to free up RAM.
And garbage collection is notorious for causing its own micro stutters in the UI.
It defeats the entire purpose of offloading the work in the first place. You avoid the parsing freeze, but you introduce a memory allocation freeze.
Yep, you're just trading one bottleneck for another. And actually, Margaret mentions another advanced caveat here.
Oh.
If payloads hit hundreds of megabytes, developers need to look into streaming JSON parsers.
Streaming parser. So instead of waiting for the whole massive file, it reads it chunk by chunk.
Exactly. It prevents the memory from blowing up all at once. But even without streaming, how do you bypass the clone? How do you get the flat-pack boxes into the garage without building a duplicate set of boxes?
This is where the source material dives into high-performance, low-level browser mechanics. Margaret teaches Timothy about transferable objects and array buffers.
Yes. Here's where it gets really interesting.
So what exactly is an array buffer?
In simple terms, an array buffer is a generic, fixed-length block of raw binary data sitting in your computer's RAM.
Okay.
It is a much lower-level representation of data than a standard JavaScript string. And browsers have a special set of rules for handling them.
Meaning they don't trigger the structured clone algorithm.
They bypass it entirely through a concept called zero-copy memory transfer.
Zero copy. That sounds fast.
It is. When the main thread sends an array buffer to a web worker, it doesn't copy the binary data. Instead, it transfers ownership of the memory block.
It just hands over the keys to the garage.
Yes. The main thread instantly loses all access to that block of memory. If it tries to read the data a millisecond later, it will actually throw an error.
Oh, wow.
Ownership is cleanly severed, and the web worker gains instantaneous access to that exact same physical location in the RAM.
No cloning, no memory spikes, no garbage collection lag.
None of it. It is lightning fast and highly memory efficient, regardless of whether the payload is 50 megabytes or 500 megabytes.
So what does this all mean? We started this conversation looking at a simple visual glitch, a stuck loading spinner. And now we are talking about manipulating raw binary data ownership in the computer's physical RAM.
It really highlights how deep the rabbit hole of front-end performance goes.
It does. What users perceive as, a fast website is actually a deeply complex orchestration of memory allocation, thread management, and parallel processing.
It is the dividing line between applications that feel clunky and frustrating and applications that feel like native, deeply integrated desktop software.
Let's paint the final picture here to see how Timothy's architecture transforms. Based on Margaret's mentorship, he restructures his code. He literally splits his logic into two completely separate files.
Right. He creates a new file called worker.js. That becomes the detached garage.
Makes sense.
Inside that file, he places all the heavy lexical analysis and JSON parsing logic. He also builds in robust error handling, ensuring that if the server returns malformed data, the worker handles the crash silently in the background without taking down the main application.
And his main application file is stripped of the heavy lifting. It fires the network request, converts the response stream into a raw array buffer, and transfers ownership to the worker.
Yep. So Timothy hits save, he navigates to his dashboard, and hits refresh.
The moment of truth.
The asynchronous network request fires in the background. The massive 50 megabyte raw binary payload of analytics data arrives from the server.
The main thread transfers ownership to the web worker. And this time, the sleek CSS loading spinner never drops a single frame.
It twirls flawlessly, a perfect 60 frames per second. The application feels incredibly responsive.
The user can highlight text, click around the navigation, or scroll the page with zero resistance.
And behind the scenes, locked in its isolated execution context, the web worker is quietly, aggressively chewing through megabytes of binary data, assembling the massive JavaScript object.
A few seconds later, it transfers the finished structure back. The grid on the dashboard populates seamlessly.
The main thread barely lifted a finger. It just conducted the orchestra.
It really makes you appreciate the unseen craftsmanship in our digital tools. Think about the web applications you use daily. When you load up a massive financial spreadsheet in the browser or manipulate layers in a web-based design tool.
Figma or something similar.
Right. And it handles huge amounts of data without ever stuttering. You are benefiting from this exact invisible architecture. There is a silent sous chef working tirelessly in a background thread so your experience remains completely fluid.
Invisible design is a hallmark of great engineering. You only notice the main thread bottleneck when it's there.
Exactly.
When parallel processing works perfectly, the complexity completely disappears from the user's perspective.
We've spent this time breaking down how offloading heavy data parsing to web workers keeps our user interfaces perfectly smooth. But this raises an important question, something for you to ponder the next time you interact with a massive web application.
Yeah, absolutely.
If developers can successfully isolate and offload heavy lexical analysis into these parallel background threads, what other traditionally main thread tasks might eventually be pushed into the garage?
That's a great thought.
Could we see complex state management or heavy DOM-diffing algorithms moved entirely off the main thread? And as more and more logical complexity is handed off to background threads, how might that fundamentally change what a web browser is ultimately capable of running?